Good morning, everyone. I hope you guys are doing well this morning. I'm going to show you a couple of examples of how to solve some systems of equations today. Last week you looked at linear systems using substitution, elimination, as well as graphing in order to solve those systems. This week we're going to focus more on nonlinear systems. And just to recap a little bit, when you have a linear system of equations, you can have your two lines intersect at one point, in which case you have one solution. You can have your lines be parallel, in which case you have no solutions, or you can have overlapping lines that are exactly in the same location, in which case you have infinitely many solutions, and those solutions are all of these points that make up the line. However, this week we're going to be looking at nonlinear systems. So imagine you have a quadratic equation, and we're just going to take a simple quadratic equation, y equals x squared, for example, and let's say I have a line. Take something simple like y equals 3. If I were to look at this graphically, y equals x squared is my parent parabola function. Y equals 3 would be a horizontal line going through 3 on the y-axis, and you'll see that you've got two different solutions to this system. So we're going to be looking at how to actually solve these algebraically using substitution, as well as solving them using a graphing calculator or Desmos. So this is a case where you've got two solutions. Again, imagine you have a parabola, and this one I'm just going to draw it out over here. And let's say your line just barely touches that point and is tangent at that point, in which case you would only have one solution. Or if you had the line going through the vertex and it's a horizontal line, that would also give you one solution. Or if you have this quadratic, and let's say your line is somewhere out here, in which case they never intersect, so you would have no solutions in this case. So you will still have some special cases, and depending on the type of function you have, you may have more than two solutions. An example of that would be, let's say you have a cubic function, and then you've got a line going through. You'll see 1, 2, and 3 different points of intersection. So you can have as many solutions as you want, depending on the type of function you have. Okay, so let's get started with a system that I'm going to show you how to solve graphically. Now you should be able to use your graphing calculator, and using the calculate option for intersect, find the exact point of intersection. I'm going to demo this with Desmos today. For some reason my graphing calculator is not working, but take this system, and as I'm going through these, feel free to pause and try these out on your own before you see the solution. So I've got y equals 3 minus log of x and negative 2x plus y equals 1. Go into Desmos and equals 3 minus log of x, negative 2x plus y equals 1. So we see our log curve here. That's the red line, and then you'll see the blue is the linear. Here's the point of intersection at 1, 3. So the solution is the ordered pair 1, 3. And I know this is not going to have more than one solution, because if I look at the log graph, I know that this is an asymptote here, so it's not going to do anything funky on the left. And then on the right-hand side, I know this is going to decrease indefinitely, and obviously the line will not turn around and meet with this log function again. So I know this is my only solution right here at 1, 3. Again, you should be able to do that using your graphing calculator. For now, I'm just going to jot down the solution. There we go, 1 comma 3. It gets a little more interesting when we start using algebraic methods like substitution to solve these systems. So I have this system, negative 2x plus y equals 5. That's a line. And x squared minus y plus 3x equals 1. We know that's a quadratic. So just thinking about what these functions are help you in the process when you're solving it in terms of expecting how many solutions. So we know we're going to get either one solution, two, or no solutions, depending on how this looks. And we'll look at the visual in a minute. Let's actually solve this algebraically. So using substitution, I like to start with the more easier looking equation. So the line is obviously a cleaner equation than the quadratic is. So I'm going to take that negative 2x plus y equals 5 and solve for either x or y depending on which one's easier. So you don't necessarily have to solve for y. In this case, it is easier to solve for y by adding 2x to each side. So y equals 5 plus 2x. Now we're going to take that expression for y and sub it into the second equation for y, being extra careful because of the negative sign in front of the y. So anytime you substitute, please make sure you put parentheses around your expression as to avoid any mistakes with substituting and distributing this negative. So now I'm going to take this equation, solve for x, distribute the negative sign in there, combine like terms. So I've got these two x's. I'm also going to subtract the 1 at the same time. So x squared, put it in standard form, that'll be 1x. And then subtract the 1 from the negative 5, so that'll give us a negative 6 equals 0. That's a nice quadratic that I can factor pretty easily into x plus 3 times x minus 2. So my solutions for x are negative 3 and positive 2. Now keep in mind when I'm solving a system of equations, I'm looking for an ordered pair, a point where the two graphs intersect. So I have the x values. I still need to find y. So looking at each of these x values one at a time, I'm going to take, let's see, the easier equation, the linear equation, and substitute the negative 3 for x. In fact, I'm going to cheat a little bit and use the one that I've already solved for y because it's slightly less work. So that'll give me y equals 5 minus 6 is negative 1. So that is the ordered pair, negative 3, negative 1. And then if x were 2, y equals 5 plus 2 times 2. Again, I'm subbing it into the linear equation, the first one that I had solved for y. So that's 5 plus 4 is 9. The ordered pair here is 2, 9. And those are my two solutions. If I look at the graph of this, I think I have it graphed already. Here it is. You can see your two solutions at negative 3, negative 1, and positive 2, 9. So got the quadratic and the linear intersecting twice. All of these you can check by graphing on Desmos or on your calculator to make sure you're doing the algebra correct.